Hey everybody, welcome back. This is the start of the second semester of the year. It's hard to believe that we are halfway through the year now, and we have another half that is coming. Um, you may be curious what all it is that's coming. We'll kind of highlight some of that stuff pretty soon, but hope the exam went okay. I think Miss Baribeau has probably let you know that I am still out of the country. I hope to be able to pick up those exams today. I should arrive late last night or early this morning, and should be able to pick up those exams and the homework that you've been turning in, get those graded, and get that back to you tomorrow so that you have your end of semester grades by Thursday. So thank you again for your prayers for my work and the trip that I was on. I'm continuing to pray for you guys as well. The section we're going to be doing today, we're actually going to be doing it today and tomorrow, so Thursday, Tuesday and Wednesday, is curve sketching. And this section actually brings together a lot of previous stuff that we've done, which is why I was hoping to get to it prior to the exam. But that didn't quite work out because we had a snow day or a sewage day or something. So instead, we're going to run through it today and Wednesday. I like this section in that it, like I said, it brings a lot of things together. You start to see pieces that we've been studying all come together in one thing. On Thursday, we'll take another application of derivatives differentiation, which is called optimization. It actually goes back to one of the questions at the beginning of Chapter 3. How do we find the best, the top, the bottom? How do we maximize profit, minimize cost, things like that? That's to come, and we'll actually spend 2 sections on that as well. So one of the things that Ms. Baribeau will hand out to you is a checklist for curve sketching, and you'll probably already see a typo there, sketching, but it's curve sketching. There are, when I give you a function, when I give you the formula of a function and I ask you to graph it, there's actually 8 different things that I'm going to have you take a look at as we're trying to sketch. Now, you don't have to memorize all 8 of these things, but when you do the homework, and then when this shows up on a quiz or exam, I am actually going to, I'm going to give you like part A, part B, part C, so you don't have to memorize these. You do need to know how to get them. You're not going to have this checklist with you, but you don't have to memorize that. You need to look at these specific 8 things. Most of these 8 things we've already run through. If you look at them, you'll see the first part says domain, intercepts. We'll review a couple of those things. Skipping symmetry for a second, asymptotes, increasing, decreasing, local maxima, minima, concavity, inflection points. Those are all things that you have seen before. The one thing on here that we briefly talked about, but not really a lot at the beginning of the semester, but is really going to be helpful for you when you're doing sketching curves, is symmetry. So I want to go through that here real quick. I just want to review symmetry. What is symmetry? I just want to take maybe 5 minutes, talk about it, talk about what it looks like graphically, talk about what it looks like with a formula. Once you get that, then the problems that we're going to be looking at will actually be a lot easier to deal with. So let's just talk real briefly about symmetry. So symmetry. Okay, this idea is related to the idea that we had at the beginning of the semester where we were doing transformations of functions, so shifting up and down or left or right, stretching, compressing, and reflecting. It actually has to do a lot with that reflecting concept. So the idea of symmetry, the terminology comes from, well, let's actually just do an example and you'll see. First of all, you'll see what it is that I'm talking about. So with this concept, just like with other concepts in calculus, there's always a graphical understanding, a way that you can graphically see what's going on, and then a formula. So let's start with the function x squared. One of the things you'll notice about x squared is it looks the same if you flip it like this. So we call this symmetric about the y-axis. Okay, that means it looks the same if you flip it around the y-axis. From a formula standpoint, flipping around the y-axis means plugging in negative x. And one of the things you'll find when you plug negative x into the function x squared is that the negative gets squared out and you get the original function. So when you flip it, when you plug in negative x, you actually get the original function. So because this happens not just with x squared, but any even power of x, when this happens, in other words, when you plug in negative x into a function and you get the original function back, we call that being an even function. And when a function is even, it looks the same if you flip it around the y-axis. Okay? Let me maybe give you another example here just so you can kind of see this. Let's take the function x to the fourth plus 2. I'm just making up something, okay? X to the fourth looks a lot like x squared. But in this case, we're shifting up 2, and it's kind of a little more shallow and then gets steeper quick. If you plug in negative x in this, again, what you'll see is that we get negative x quantity to the fourth plus 2. That's just x to the fourth plus 2, and that's just the original function. So we say that this function is even because when we plug in negative x, we get the original function because the graph of it looks the same around the y-axis. Okay, so these are even functions. Okay. Now if we were to take an odd power of x, let's look at, for instance, x cubed. One of the things you'll notice here when I graph this is that this doesn't look the same. I'm going to draw it really great. It does not look the same if I flip it around the y-axis. However, it does look the same if you flip it 180 degrees. So in other words, if you were to take just kind of turn your head upside down and look at it that way, flip the graph around 180 degrees, it looks the same. So if we were to turn it 180 degrees around the origin, it would look the same. So there's a terminology that sometimes people use. They would say this is symmetric about the origin. What that means is if you flip it around 180 degrees around the origin, it looks the same. Okay. So let's look at what happens if we plug negative x into this function. What you'll find is when you plug negative x in and you cube it, that negative does not go away. It actually stays there. And so then negative x cubed is the negative of the function. When this happens, plugging in negative x gives you the negative of the function. We're going to say that the function is odd. And that terminology odd comes from the fact that this works with odd powers of x. It's not always an odd power of x where this happens, but because it happens with odd powers of x, we're going to call it odd. So odd means an odd function looks the same if you spin it 180 degrees. And algebraically, if you plug in negative x, you get the negative of the function. Okay? So maybe as another example here, let's take the function x cubed minus x. All right? Okay, so this ends up looking like that. There's no reason you need to know that it looks like that right now. But you'll notice, again, this looks the same if we were to flip upside down 180 degrees or spin it. Okay? And if we plug in negative x, what we see is everywhere there's an x, we're going to stick a negative in there. And what we get is negative x cubed plus x, and that again is the negative of our original function. So we're going to say, when that happens, our function is odd, and it looks the same if we spin it 180 degrees around the y-axis. Okay? So a function's even if, when we plug in negative x, we get the original function, and that means graphically it looks the same across the y-axis, like a mirror image here. It's odd if we plug in negative x and we get the negative of the original function, and graphically that looks like spinning it 180 degrees. Gives you, looks the same. Now the reason that we care about this when we're graphing functions is that if the function looks the same on the right and the left sides, then that kind of cuts down on the work that I need to do. I only need to do, for instance, what's on the right side, and then I'll kind of know what's going on the left side. Or it can serve as kind of a check to tell me, did I do my work correctly? Same if I know the function's odd, and I do the right side work, I can flip it around and that would give me what the left side work looks like. So for instance, if I have an odd function and I have a vertical asymptote here, then I know I'm also going to have a vertical asymptote over here because of the symmetry that's going on. Let me show you just a couple of other examples here. Okay, for instance, let's take the function sine of x, and you should be familiar with the graph of that. Okay, one of the things that you'll notice is that if you were to spin this 180 degrees, it looks the same, which means that sine is an odd function. And that means if I were to take negative x and plug it into the original function, I should get the negative of the original function. That's what happens with odd functions. Okay, another example of an odd function that you are familiar with but might not think of it as odd is tangent. Okay. And I know tangent looks kind of weird here. But again, if you were to spin this 180 degrees around the origin, or you were to look upside down, this would be odd. So in other words, if you plug in negative x, that's the same thing as the negative of the original function. Both of these functions are odd. Whereas, you're probably guessing where I'm going here, the cosine function here's the cosine function. The cosine function looks the same across the y-axis, so the cosine function is an even function. And that means if you plug in negative x, you actually get the same thing as the original function. Okay, so cosine is an even function. Right? Now, one thing you need to realize, though, typically when people get introduced to the idea of odd and even functions, you think, oh, so a function is either even or odd. No, there are lots and lots and lots of functions that are neither even nor odd. They don't work with either one. So let me give you an example here. If I take the function x squared plus 2x plus 1, this function turns out to be, there's no reason you should know this, but, well, I guess you could think about factoring it. But it's x plus 1 quantity squared, which is x squared shifted to the left 1. One thing I want you to notice immediately from the graph is that it is not even. Okay, if you flip it around the y-axis, it doesn't look the same. If you spin it around the origin, it would be down here, so it's not odd. So this is, from the graph, you can see This is neither even nor odd. You can be neither. Now, one way we could check that with a formula is if we plug in negative x everywhere, so negative x quantity squared plus 2 times negative x plus 1, we end up with x squared minus 2x plus 1. That is not the original function, and it's not the negative of the original function. So because it doesn't match the original function, it's not even. It doesn't match the negative of the original function, so it's not odd. So it is neither. So when you're looking at symmetry, you could have a function that is even, it could be odd, or it could be neither one. All right, so just be careful of that when you're checking symmetry. But again, the idea of putting symmetry in this list is when we're graphing functions, when we're going to stick a function on an axis, it's helpful for us to know, here's what's going on the right side, here's how it interacts with what's going on the left side. Okay? So that's just a little tiny tidbit about symmetry. What we're going to do now is we're actually going to run down this list for 3 examples today, and then tomorrow we're going to look at 2 more. If we finish the 3 early, then you're just going to have time to work on your homework. I will warn you that these problems, it might seem like the homework is very short because there's only like 6 problems or 7 problems, but these problems are long because they have, as you can see, they have 8 parts to them. So don't underestimate these the problems here. Okay. And I think you got your handout from last week on what the homework is for this week. There's only 1 homework assignment. It's due on Wednesday. We'll have a little bit of flexibility in letting you turn that stuff in on Thursday if you get behind. But please, please, you need to make a lot of progress on that for Wednesday. Yeah. So we're going to look at 3, like I said, we're going to look at 3 examples. The first example that we're going to look at, so we've got curve sketching here. And what I'm going to do in each of these examples is just run down that list of all of the things that we've got here, domain, intercept, symmetry, etc. We're going to review these. So first one I want, I'm going to take the function x squared over x squared plus 3. Okay. Now my first tip when you're doing this, please graph the information as you get it onto the axes. Please do not wait until you get through all 8 of these things and then try to throw all of that information onto the axes all at once. That is really hard. It's a whole lot easier to take one piece of information at a time, put it up there, okay? So the first thing we're gonna look at is domain. Okay, domain means, remember the 3 things that we're typically looking for a domain is where does the bottom equal 0, if ever? Or do we have even roots? And then are there logarithms or other special functions that have strange domains? So here, the only thing we really have to worry about is the denominator, and the denominator is never 0. X squared can never be negative. So this thing can never get smaller than 3 anyway. So the domain here is actually all real numbers. Now if the domain was not all real numbers, what I would do is I would actually come over to the axes and I would scratch out certain places that I'm not allowed to graph. And that would be the reminder to me that I need to make sure I'm not graphing there. Okay? All right, next, intercepts. So intercepts are where we hit the x and y axes. So the y-intercept, and this is the thing that everybody always misses up, the y-intercept, the place where I hit the y-axis, is when x equals 0. The y-intercept is when x equals 0. The x-intercept is when y equals 0. So what I'm going to do is I'm going to take 0 and plug it into the function, and when I plug that in, I get 0. So I have the y-intercept here is at 0, 0. That's where I hit the y-axis, right there. And now the x-intercept is when y equals 0. I want to know where am I hitting the x-axis. So I set the function equal to 0 and solve. Now a fraction is only equal to 0 if the top is 0. And so that's just this same point right there. So one of the things that that tells me, actually, is that I should never cross the x-axis except right there. It might not seem like I'm graphing extra information, but this actually does give me extra information. I'm never crossing the x-axis except right at that point. Okay, looking at my list, let's look now at symmetry. Okay, what I do for that is I always plug in negative x everywhere where there's an x, making sure I use parentheses. And what you'll notice is that because everything's squared, I just get that original function back. So that means that this function is even. It's going to look the same when I flip it around the y-axis. That's going to be really helpful information for me. All right? Okay, so the fourth thing that I'm going to look at is asymptotes. And we're going to start with vertical asymptotes. And vertical asymptotes, I'm looking typically for issues with the domain. In this case, I have a polynomial over a polynomial. That bottom thing never is 0, so I have no vertical asymptotes because that function is actually continuous on the entire domain. So I don't have to worry about vertical asymptotes. Now to look at horizontal asymptotes, if you remember from what we talked about in the review, you look at two limits. You let x go to infinity, and then you let x go to negative infinity. When x goes to infinity, okay, I look at the highest power of x on the bottom, and I divide the top and bottom by that. So I'm going to divide by x squared. And what I get here is on the top I get 1, and on the bottom I get 1 plus 3 over x squared. And that term ends up going to 0. So that limit just ends up being 1. Okay. Same thing happens when x goes to negative infinity. Okay, that's the work is exactly the same, so that limit will also be 1. So the horizontal asymptote that I have is y equals 1. So I'm going to go over here and I'm going to graph that horizontal asymptote. Okay. And I don't know how the function approaches 1. It could come in from the bottom like that. It could come in from the top. It could technically, I guess, squiggle in like this. But eventually I'll fix that. But I want to just sort of represent to myself, yes, I need to, on both sides, I need to approach 1 when x goes to infinity or to minus infinity. So I'll fix whether it's coming from the bottom or the top when I get more information. All right? So I've got those 4 pieces of information so far: domain, intercept, symmetry, and asymptotes. The rest of what I'm going to do here is just looking at what we've typically looked at in section 3.3 and section 3.4. Increasing, decreasing, local maxes and mins, concavity, and inflection points. And yes, quotient rule. That's what we're going to get here. Okay? So let's take a look at that. So let's look at increasing and decreasing first. And that's going to mean we need to take the derivative. So we've got low d high minus high d low. And then we square the bottom. Okay. Multiplying out, we actually have something nice happen. 2x cubed plus 6x minus 2x cubed. So thankfully the top here actually becomes simpler. We just get 6x over x squared plus 3 quantity squared. Okay. And then we ask like normal, two questions. Does this ever not exist? We don't have any issues because the denominator is never 0. When is this equal to 0? Well, a fraction's only 0 if the top is 0. So if 6x equals 0, that means x equals 0. So in terms of the derivative is only, we only have a critical number at x equals 0. Everywhere else, here's the derivative that we're plugging into. When x is positive, the bottom is always positive. It's something squared. When x is positive, the whole thing is going to be positive. When x is negative, the top is going to be negative. The bottom will be positive. Okay? So that gives us our derivative. That tells us what's happening in terms of increasing and decreasing. So I'm increasing on the interval from 0 to infinity. I'm decreasing on the interval from negative infinity to 0. I have a local min at x equals 0 and no local max. Now I need to take this information and actually graph it. So what I'll notice here is I have a local min at x equals 0. That means I look something like that. And then I'm increasing on the right side and decreasing on the left side. So notice, for instance, I know I'm increasing over here, so I can't go up and then down to the asymptote. So that tells me that these probably connect this way. And I'm decreasing on this side, so that tells me that these things probably connect this way. Now how they curve, that's what we're going to deal with in just a second here. Okay, but we already kind of have an idea of what that function looks like. So that's good. We're close. Okay, so now all we've got to deal with is concavity. So let's do that. All right, so we'll take a second derivative. Here's my first derivative. So let's differentiate from there. So the second derivative is low. Derivative at the top is 6. Low d high. Minus high. And then the derivative of the bottom, I get 2 x squared plus 3. And then I've got times the derivative of the inside. It's a chain rule. I've got a 2x there. And then all of that is divided by the bottom squared. So I've got 4 copies now of x squared plus 3. So now one of the things that you notice, to try to simplify, everything has an x squared plus 3 in it. This term does right here. This term does, and this term does. So now what I'm going to do is I'm going to cancel one of those in each of the terms on the top with one of these on the bottom. That's going to leave 3 of them on the bottom. Okay. And so now on the top what I have is 6x squared plus 18 minus, I've got 6 times 2 times 2, that's 24x squared. And the bottom is still x squared plus 3 cubed. Now if I simplify that more, I've got 18, I've got minus 24x squared, and plus 6x squared is 18 minus 18x squared. And you'll notice I can factor an 18 out, and I get 1 minus x squared on the top there. Okay, so I realize that's not so fun, but we got our answer. It's not too bad, actually. And now I ask the same question that I asked over here. Where does this not exist? We actually have no problems, again, because the denominator has no issues. This equals 0 when x is plus or minus 1, when x squared is 1. So I'm going to graph that on a number line now. So the second derivative is 0 at those 2 points. And then checking things around there, if I plug in 0, this top thing is positive and the bottom thing is positive, so the whole thing's positive. The bottom's actually always going to be positive again. If I plugged in 2, the top would be negative and the bottom would be positive. So I get a negative here, same for negative 2. So that means I'm concave down on these outer intervals and concave up on these inner intervals. So I'm concave up from -1 to 1. I'm running out of room here. Let's stick this over maybe right here. I'm concave up from -1 to 1, concave down from -infinity to -1 and 1 to infinity. Okay. And what I'm going to have inflection points at these 2 points. Now remember, the key thing with inflection points has to be a coordinate. So if I were to plug 1 back into this function, I would get 1 over 4. So I'm going to have an inflection point at 1, 1/4. And at -1, 1/4. So if I were to graph those up here, at 1, 1/4, and -1, 1/4, in between those I'm curved up, and then I start curving down. And that makes sense because I need to approach that asymptote. So I'm going to have to be curved down out there and curved up in the middle. Okay? So that is the sketch of my function based on all of the information that we've gathered here. Okay? All right. Let's see. So why don't you go ahead and take 5 minutes, take a break, and come back. I'll erase here, and we'll jump into 2 other examples that we have today. Okay. So we are back. Let's take, we're going to do 2 more examples here. Sorry, we've got at least 1 more that's going to be a fraction. Our third one's not going to be quite this bad. Okay, so let's start out here again with same questions. So here for the domain, we're looking at, since we have a fraction, we're looking at where does the bottom not equal 0? Or where does the bottom equal 0? So in this case, the bottom equals 0 when x is plus or minus 1. And so we don't want that to be happening in the domain here. So what that means is we'll come over to our graph. And at 1 and -1, I'm going to scratch those out just because I don't want you graphing anything there. So we just have to kind of tell ourselves, make sure we're not graphing anything there. All right, if I look at intercepts, so the y-intercept is when x equals 0, and when x is 0 and I plug that in here, I just get y equals 0. So again, my intercept right here is 0, 0. The x-intercept is when y equals 0, so we set our fraction equal to 0, and a fraction's only 0 if the top is 0, so we get x equals 0, we get that same thing. So just like before, the place where it's crossing the y-axis is at 0, 0. it's only crossing the x-axis at 0, 0. So I better not have a situation where I have some information that's forcing me to cross an axis somewhere else, because this says that's not supposed to happen. Okay, you'll find all these double checks happening when you're doing curve sketching. All right, now let's look at symmetry. And again, remember what you do is you plug negative x in and see what happens. So if I plug negative x in everywhere, I get negative 2x on the top, but the squared part doesn't change the bottom. And I'll notice this is actually the negative of the original function, so that means this function is odd. In other words, it's going to look the same if I rotate it 180 degrees, and you'll notice already that there's information on both sides, at 1 and negative 1, which seems to show some sort of nice symmetrical stuff that's going on here. Okay, let's look at asymptotes next. Here we're going to be pulling out some stuff from our previous, since we're talking about limits. So the candidates for vertical asymptotes are 1 and negative 1. So I'm actually going to have to look at the limit as x goes to 1 of the function and the limit as x goes to negative 1. But if you remember when we did this earlier, the top, so when x goes to 1, the top goes to 2 and the bottom goes to 0. That means it's infinite, so this will have a vertical asymptote there. But I'd actually like to graph it, so I need more information. And when we did this before, when we were talking about limits, what we did was we actually went from both sides. So we went from the right side, and then we went from the left side. Okay. So when I go from the right side, if x is bigger than 1, this bottom part is actually positive, and the top is already positive. So when I go to 1 from the right, this fraction's going up to positive infinity. So in other words, here's my asymptote. As I come to 1 from the right side, the function's going up to positive infinity. That's what that information tells me. Okay, whereas down here, if I'm coming to 1 from the left side, if I'm smaller than 1, this x squared is smaller than 1, so the bottom is actually negative, whereas the top is positive. So on the left side, as I come to 1, the function actually goes down to negative infinity. Okay, so that's what that looks like graphically. Now I am going to work out what's going on with when x goes to negative 1. But if this is even, sorry, if it's odd, then when I spin this, what should end up happening is what's down here ends up coming up here. So I should see this happening when I come to negative 1 from the right side, it goes up. And if I spin this asymptote over, when I come to negative 1 from the left side, it should go down. I should see this same thing if it's going to look the same when I spin it. Now let's just check that by looking at the limit as x goes to negative 1 from the right and the left sides. Okay, so again, when x goes to negative 1, the top goes to negative 2. And the bottom goes to 0. If I'm to the right of negative 1, I'm kind of smaller than negative 1, smaller fraction. This bottom is also negative, and so I have a negative over a negative gives me a positive infinity, and that's what I'm seeing up there. Whereas if I come from the left side, the top's going to negative 2, the bottom is going to 0, but if I'm a number that's to the right of negative 1, like negative 2, when I square it, I get a big number here, so that ends up giving me a positive on the bottom and negative on the top. So overall, I get a negative infinity there. Okay, and that matches what's going on over there. So that tells me the vertical asymptotes. So I have vertical asymptotes at x equals 1 and x equals negative 1. Those are my vertical asymptotes. For horizontal asymptotes, we always only need to look at two limits. The limit as x goes to infinity of the function, and the limit as x goes to negative infinity of the function. Typically, in many cases, these give you the same limit, not always. In this case, we divide by the highest power of x on the bottom, which is x squared. And so on the top, I get 2 over x. On the bottom, I get 1 minus 1 over x squared. So this top goes to 0, and the bottom goes to 1, so the limit here overall is 0. Same is going to actually be true for the negative infinity one. So I have a horizontal asymptote of y equals 0, and that means I'm approaching, again, I don't know if I'm approaching from the top or the bottom. If I had to guess, I'm guessing from the bottom here and the top here, but it could technically go down and then come back up, for example. So, sorry, my computer keeps falling asleep, but I have the video continuing to run. So, okay, so that gives me all the asymptotes. Now let's look at increasing, decreasing. Again, you can already kind of predict. This is probably decreasing, decreasing, decreasing would be my guess. We need to check that. So let's do a derivative. Okay, we've got low d high minus high, and then the derivative of the bottom is 2x. X squared minus 1 squared. So I've got 2x squared minus 2 minus 4x squared. Okay, and if I clean that up, that's minus 2 minus 2x squared. So I can actually pull a minus 2 out on the top, and I get 1 plus x squared. And the bottom is x squared minus 1 squared. Okay, so what I ask then here, just like always, I ask two questions. Where does this not exist? Where does it equal 0? It does not exist at negative 1 and 1. Because the denominator is 0 there. There's no place where this, if I were to set this fraction equal to 0, there's no place where this top equals 0. So these are going to be my only critical, or my only places where the derivative doesn't exist. These aren't critical numbers because they're not in the domain. So something to be careful of here. If I plug really anything in here, the bottom is positive. I've got a negative here, and this thing is always positive. So your negative times positive times positive, all of these are going to be negative, in which case I'm decreasing on all of those intervals from negative infinity to negative 1 to 1, and then 1 to infinity. So there are no local maxes or mins. Okay, and I can tell on my graph now that this thing down here should be decreasing. I should be decreasing here. And I should be decreasing here. Not that. Okay. So now you can probably also guess the concavity that's going on here at this point. It looks like I'm concave down, concave up here, concave down, and concave up. So let's just confirm that, and then we'll be done. All right. So for our concavity, let's take, this is our second derivative. Sorry, our first derivative. So let's differentiate that. Okay. So the second derivative, I've got, let me back this to the left just a little bit. So I've got low d high, the derivative of the top is just negative 4x minus the top times the derivative of the bottom. So the derivative of the bottom, I'm going to get 2, I've got a chain rule, 2 times x squared plus 1 times 2x there, times the derivative of the inside. All over the bottom squared, which means I have that to the 4th power. Okay. Again, like before, this term right here, this term right here, and this term right here all have an x squared minus 1. So I'm going to cancel one of them. This happens a lot with quotient rules when you're looking at the second derivative. It makes things a little bit easier. So what I have here, if I clean this up some, I've got negative 4x times x squared, negative 4x cubed, plus 4x, so that takes care of these two. All right, and then I've got a bunch of minus signs, so I've got minus is plus, 2 times 2x gives me plus 8x. And then minus again gives me plus 2 times 2 times 2, 8x cubed. X squared minus 1 cubed on the bottom. So combining things a bit more, I've got 4x cubed plus 12x on the top. And I can factor that. I can factor out a 4x, and I'm left with x squared plus 3. Okay, so that is my second derivative. So now I'm going to graph, where does this not exist? Where does it equal 0? So it doesn't exist again at negative 1 and 1. If I look at where does this fraction equal 0, again, a fraction's only 0 if the top is 0. This term right here, x squared plus 3, is never 0. So the only place where that fraction is 0 is at x equals 0. And if I check around these points, okay, if I take something really big, the top is going to all be positive, the bottom's all going to be positive. So we're positive there. If I were to take something like a half, the top is still all positive, but the bottom becomes negative because I have something negative that's cubed, so I get a negative overall there. Taking something really big negative, like negative 10, this first part's negative, second part's positive, third part's positive, so I get a negative there, and then a positive here. So I'm concave down on 2 of those intervals and concave up on 2 other ones. So I'm concave up from negative infinity to 1, sorry, from negative 1 to 0, and from 1 to infinity, and I'm concave down from negative infinity to negative 1, and from 0 to 1. Now notice that I don't get inflection points at 1 or negative 1. The only inflection point that I get is 0, 0, because the function doesn't exist at negative 1 and 1. So that seems to confirm we're concave down, then concave up, then concave down, then concave up. Notice it doesn't level off, because if it leveled off here, the derivative would be 0 and we'd get something there. We don't get that, so it doesn't level off. But we still, it follows all of those pieces. Okay? So that is our graph of this function here. Phew. Okay, we're going to do one more example, and then we'll set things aside for the day. No complaining about the quotient rule. I know it's not fun, but if we didn't have it, we couldn't even get this stuff, so. Okay, last example we're going to do today is 3x cubed minus 9x plus 1. Right? Not too bad. We'll end the day with something that's not overly crazy. Okay, so let's start with domain. Let's go down our list. This is a polynomial, so its domain is all real numbers. We have no issues here. It's actually continuous everywhere. It's actually differentiable everywhere. For intercepts, again, we look at the y-intercept, which is when x equals 0, and when x equals 0, the function is 0, 0, the function is 1. So my y-intercept is at 0, 1. Now, I'm trying to remember I don't know the scale of this function, so I'm not going to make that too high there. Now for the x-intercept, I actually have to set y equal to 0, and so I need to set this function equal to 0. Now, I'm going to freely admit here now, there are some functions you're going to run into where there probably are x-intercepts. In other words, there's a way to solve this, but we don't have good factoring techniques to solve this. So there are going to be times when we get something that's just too hard to solve. Okay, if you can immediately factor it, if you can't set it equal to 0 and solve it pretty easily, don't spend a lot of time trying to figure out how you're going to get the x-intercept. So we don't have the information here. It may cross these axes, and I just don't have information regarding what's going on here. Okay, we'll come back and talk about that a little bit. For symmetry, all right, I plug in negative x everywhere. So in the cubed, in the x, and there's nothing there in the 1. So when I multiply this out, I get negative 3x cubed plus 9x plus 1. And so one thing you'll notice here is that when this is not the original function, because obviously some of these signs have changed, but it's not the negative of the original function because the sign on the 1 didn't change. Okay, so there's no symmetry here. It's not even, it's not odd, we just don't have anything going for us here. We can't use symmetry here. Okay. All right, let's look at asymptotes next. There are no vertical asymptotes. Can you figure out why? Yeah, the function is continuous. So there's no, we're not going to have any issues here. For horizontal asymptotes, again, we always look at what happens when x goes to infinity. What happens when x goes to negative infinity? All right, and when x goes to infinity, this first quantity becomes much, much, much larger than anything else. If you imagine plugging 1,000,000 in here, 1,000,000 cubed is much, much, much bigger than 1,000,000. So this first part goes to positive infinity. When we go to negative infinity, this is like negative 1,000,000 cubed, which is going to give you a much bigger negative number than what's going to show up here. So on the left side, this function's going, when x goes to negative infinity, the function's going down to negative infinity. When x is going to positive infinity, the function's going up to positive infinity. Okay. I don't know exactly how that's working, but that's the information that comes from looking at limits here. All right. So now let's let's do increasing, decreasing. So we're going to differentiate, and when I differentiate, I get 9x squared minus 9. All right, and then I ask, where does that not exist? Where does it equal 0? Obviously, there are no places where this does not exist. If I set this equal to 0 and factor a 9 out, we can see that we're looking at x equals plus or minus 1. So at negative 1 and 1, the derivative is 0. Here's the derivatives right here. So if I were to plug in 0, I'm going to get a negative number. If I plug in a really big number, like 10, I'm going to get a really positive number. Same if I plugged in negative 10. So that means the function's increasing, then decreasing, then increasing. So we're increasing on the interval from negative infinity to negative 1 and 1 to infinity. And we're decreasing from negative 1 to 1. And we're obviously then looking at a local max at x equals 1 and a local min at x equals negative 1. And since we're graphing, we actually need to graph what that is. So we're going to plug 1 in, plug it back into the original function. Here we're going to plug 1 back into the original function, and what we get is 3 minus 9 is negative 6, plus 1 is negative 5. And when I plug negative 1 in, I get negative 3, plus 9 is 6, plus 1 is 7. So, I've got these switched, I just realized that. I have a local min at x equals 1, and the local max at x equals negative 1. I might have said it, but then wrote it wrong. I apologize for the confusion here. So a min at 1 and a max at negative 1. So let's graph these. At negative 1, I'm 7. So negative 1, 1, 2, 3, 4, 5, 6, 7. And I'm a max there. And then at 1, I'm at negative 5. 1, 2, 3, 4, 5. And I'm a local min there. And it appears to be decreasing, then increasing, and then it's increasing over there. So that's kind of the overall look of our function right now. Let's just do concavity and we'll be done. Okay, so we're going to look at the second derivative. And the second derivative here is just 18x. And that equals 0 when x is 0. Okay, and testing around, when x is positive, that's positive. When x is negative, that second derivative is negative. So we're concave up on the interval from 0 to infinity. We're concave down on the interval from negative infinity to 0. And so then we must have an inflection point at 0, 1. So that means this doesn't curve out like that. It actually is curving up, 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 up. It continues to curve up. And over on this other side, it's curving down, 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 and it continues to curve down. So that is my function. All right. Great work, everybody. Again, please take a look at the homework. If you've got some time now, go ahead and take a few minutes and look through it. And I'll catch you tomorrow on Wednesday. We'll do a couple more examples, actually just 2 more, and then you'll have plenty of time to keep working on more homework problems. All right, thanks everybody.